For over a century, beginning around 1916, physicists have been captivated by black holes, some of the most powerful yet elusive phenomena in the universe. Despite their immense power, black holes are nearly invisible to us. In recent decades, we've made significant strides, transforming our understanding of them from almost complete ignorance to up-close exploration. Now, scientist Michio Kaku has announced that we have finally managed to capture a glimpse of what lies within a black hole. This groundbreaking discovery provides new insights that might alter our understanding of the cosmos. Join us as we dive into the enigmatic world of black holes and explore what researchers have uncovered about them. While space is vast, black holes stand out as regions of such intense gravitational pull that even light cannot escape them. Before delving into Kaku's findings, it's worth revisiting the origins of our understanding of black holes. Although many are somewhat familiar with the concept, there are still significant gaps in our knowledge. In 1916, Albert Einstein published his theory of general relativity, which first predicted the existence of black holes. At the time, black holes were purely theoretical. It wasn't until the 1960s that the scientific community found evidence that black holes actually exist. This pivotal moment came when astronomers observing the Cygnus constellation noticed an unusually bright blue star emitting X-rays. Unlike a typical star, this one was orbiting an unseen massive object. Further investigation revealed that the X-rays were being pulled into an invisible gravitational powerhouse, a black hole. This discovery, involving Cygnus X1, provided concrete proof that black holes are real and not merely theoretical constructs of Einstein's imagination. It also opened the door to a whole new field of study. The Cygnus X1 black hole, located approximately 6,000 light-years from Earth, shines with a brightness over 1,000,000 times that of the Sun. Its incredible density gives it an immensely powerful gravitational pull. The gravitational force is so strong that even light cannot escape, which is why it's called a black hole. The concept of a black hole is both fascinating and terrifying, as anything that ventures too close is pulled in, never to escape. This air of danger only makes studying black holes more crucial for scientists. Following the discovery of Cygnus X1, researchers began looking for other black holes and found that the Milky Way alone may contain over 100 million of them. However, their elusive nature makes pinpointing them challenging. Even so, it's clear that millions of black holes likely populate our galaxy, making them essential objects of study. The most striking aspect of black holes is their intense gravity. Anything pulled into a black hole is compressed to an extreme point, known as a singularity. In simpler terms, black holes act like cosmic vacuums that consume everything in their vicinity. Research on black holes has revealed that if someone were to fall into one, they would experience a process called spaghettification, where they are stretched thin like a single line. Eventually, the gravitational force would be too much to survive. In 2021, scientists released the first clear image of a black hole, specifically the M87 black hole. This image was captured over several nights, with each frame adding to the overall clarity. By piecing the images together, researchers identified 3 distinct layers within the black hole. The first is the event horizon, the point of no return. Once something crosses this boundary, escape is impossible. Beyond the event horizon lies the photon sphere, where light itself orbits the black hole, trapped by its gravitational pull. The innermost layer is the singularity, where matter is compressed infinitely and the known laws of physics no longer apply. This breakdown of physics makes black holes all the more mysterious and challenging to study. Moreover, each black hole has unique characteristics, meaning that no two are alike. While black holes generally follow the 3-layer model, their internal workings can vary greatly. Unlike other cosmic objects, black holes defy traditional scientific investigation. Sending a probe like Voyager into a black hole is impossible, as anything crossing the event horizon is inevitably pulled into the singularity. Consequently, researchers are left to study black holes indirectly, observing the radiation they emit and the gas and dust around them. This limits our perspective, reducing 3-dimensional phenomena to 2-dimensional analyses. These obstacles are compounded by the fact that each black hole is unique, and the laws of physics break down near the singularity. This means that conventional methods of scientific inquiry are often insufficient when it comes to understanding black holes. Despite these challenges, scientists have developed various theories and explanations that continue to shed light on the nature of black holes, making each new finding increasingly fascinating. One of the most compelling theories involves the formation and behavior of black holes themselves. Are formed from the remnants of massive stars. When a star exhausts its fuel, it no longer generates enough energy to counteract gravity's inward pull. As a result, the star begins collapsing in on itself, becoming denser and denser. If the star is massive enough, this process continues until it turns into a singularity. To understand black holes better, NASA researchers focused on the core of galaxy M87, where astronomers observed a powerful whirlpool of hot hydrogen gas spinning at an astonishing speed of 1.12 million miles per hour. The intense force of this spinning disk should have torn it apart, but it didn't. Scientists concluded that a massive object at the galaxy's center was keeping it intact, an object estimated to weigh 2 to 3 billion times the mass of the Sun, which could only be a black hole. This discovery isn't the only theory about black holes. In 1963, New Zealand mathematician Roy Kerr used Einstein's gravity equations to provide a model for rotating black holes. Kerr demonstrated that a spinning black hole would not collapse into a single point as previously thought but would form a ring. The disk would spin so rapidly that centrifugal forces would prevent it from collapsing entirely. This spinning disk of matter is called the ergosphere, the region around a black hole where the laws of physics begin to break down. Kerr's model also predicted the existence of an Einstein-Rosen bridge, or a wormhole, a theoretical passage through spacetime that links different regions of the universe, or even parallel universes. This implies that instead of being crushed to nothingness, objects falling into a black hole might be transported through a tunnel and emerge from a white hole in a parallel universe. To grasp how this works, we need to understand spacetime in Einstein's theory, where space and time are interconnected, forming a four-dimensional fabric called spacetime. Objects with mass bend this fabric, creating gravitational fields that pull other objects toward them. Imagine a piece of paper representing spacetime. Placing 2 points on the paper and drawing a line between them represents the path objects travel through spacetime. Now, if you could fold the paper and create a shortcut, that would be a wormhole, allowing for faster-than-light travel between 2 points in the universe or even between different universes. However, this is still theoretical, and while wormholes present intriguing possibilities, there is no evidence that they exist or could be used for travel. Adding to this, physicist Leonard Susskind, a pioneer of string theory and holographic theory, introduced a new perspective on black holes. His holographic theory suggests that information about everything that falls into a black hole is not lost but rather stored on its two-dimensional surface, or event horizon, the boundary beyond which nothing can escape. Susskind's theory even proposes that the universe itself might be a hologram, with everything we see and experience being a projection of information on a distant, two-dimensional surface. This idea helps reconcile the apparent loss of information in black holes with quantum mechanics, which states that information cannot be destroyed. Susskind's theory implies that black holes may not be the ultimate destroyers of information but rather its ultimate preservers. Despite these compelling theories, many questions about black holes remain unanswered. This is where physicist Michio Kaku's latest announcement becomes relevant. Kaku, known for his work in string theory, recently stated that we might finally have a glimpse of what's inside a black hole. According to him, data gathered over the years has enabled researchers to create a detailed model of a black hole's interior. This model suggests that black holes aren't empty voids but contain a complex, dynamic structure. Kaku's model posits that black holes are filled with a dense, superheated plasma in constant motion, generated by the intense gravitational forces compressing matter to extreme densities and temperatures. This plasma emits high-energy radiation detectable by telescopes. The model also suggests that the singularity at the center of a black hole is not a point but a ring or disk surrounded by swirling plasma, which is kept in perpetual motion by gravitational forces. Kaku's model has profound implications for our understanding of black holes. It suggests that black holes are not just endless vacuums that pull everything in but are dynamic, complex objects with far more going on inside them than previously thought. Kaku's findings also raise intriguing questions about the nature of the universe and spacetime. If black holes contain a dynamic and intricate structure, it hints that the universe itself might be more complex than we once believed, possibly even influencing fundamental forces like gravity. While Kaku's announcement is significant, it's important to note that it remains a theoretical model. We have yet to gather direct evidence of a black hole's interior, and much more research is needed to confirm these findings. Nevertheless, Kaku's model represents a significant advancement in our understanding of black holes and the mysteries they hold. In conclusion, our knowledge of black holes has come a long way since Albert Einstein first predicted their existence in 1916. From the discovery of Cygnus X1 to recent breakthroughs by scientists like Michio Kaku, our comprehension of black holes has advanced tremendously. While we still have much to learn, the emerging models and theories suggest that black holes are not mere voids but are active, complex entities that may hold the key to some of the universe's greatest mysteries. As we continue to explore and push the boundaries of science, we can look forward to more groundbreaking discoveries that will illuminate the nature of black holes and the fabric of spacetime itself.